We're getting towards the end. That's both good and awesome that this conference has gone so well. I'd also like to thank the Blue Waters Graduate Fellowship, without which this research wouldn't have been possible, as well as the other people that helped me with this work, especially my advisor, Anatoly, Danielle, who you just heard from, Sebastian, and of course, Joel. So the simulation set I'm going to be talking about is the VLA simulations that we've heard a lot about during this conference. These were run by Daniel Severino using the ART code. They were not selected specifically for any merger, like no late merger at redshift 1, but that's the only selection criteria on the environment or the merger history. They have a range of virial masses in the objects I'm going to be showing you. The primary halos, there's 10 of them, and they're in the mass range of 10 to the 12 to 2 times 10 to the 11 at redshift 1. So all the results I'm going to be talking about today are redshift 1. So what I'm going to be showing you is a comparison between 2 different runs of the same initial conditions. We've heard a lot about the velas with radiation pressure and supernovae feedback. The radiation pressure has only trapping of ionizing photons, no IR photons. So that was the Vela RP, which has been called Gen 3, which is also Vela version number 2, which you guys have heard about a lot throughout this conference. But very excitingly, Danielle has run the simulations again, and they've just finished. And this is Vela radiation pressure plus photoheating is what we call it. And this is radiation pressure including a photoionization term that traps the IR photons in high optical depth regions and also impacts the cooling curve. So these results are brand new, and I'm going to be showing you a comparison between these 2 different simulation runs. So for each of the 10 halos, I'm showing you all of the satellites of those halos in a stellar mass function. So we see that we have a lot of satellite galaxies at low masses, more than are observed in the Milky Way or M31. And with photoheating, we find that this number comes into a little bit better agreement with observations. We have about 5 of our host halos that have about the right number of satellite galaxies, so this is promising. But in general, it doesn't really do much to every single galaxy. So we're wondering, is this photoionization actually doing anything to these satellite galaxies? Or is it just, in general, important physics to include, but not really helping at this mass scale? And so for these plots, I've normalized all the same halo mass of 10 to the 12 so we can compare with the Milky Way. And we see that, like I said, about half of them come into agreement a little bit better than the original just velas with radiation pressure. So I'm going to show you the stellar mass-halo mass relationship, and I'm just first going to show you the comparison with other lines that we're showing. So we have abundance matching relationships shown at redshift 1 and 0 from Peter Baruzzi. We have Chris Brooks and Shay's line as well. We're comparing against some observations, and simulations are in triangles. And if we compare our data set with the various simulations and observations that I showed you in the previous plot, we see that we have a huge amount of scatter at a fixed virial mass in stellar mass and at fixed stellar mass and virial mass as well. So our dwarf galaxies around these satellites of these primary galaxies have a wide range of stellar masses, in both different sets of simulations. So it looks like when I made this plot, I was a little disappointed. I was hoping there would be some huge difference, right, between the 2 simulations. But maybe this is good. This means that we've included the most important physics up to this point, and we're hoping to find out if this stellar mass is actually something that's intrinsic to the dwarf satellites, or if it's a function of environment. So if we look at Vmax instead of halo mass, we can see that it's a little more robust against tidal stripping. So we can look at the stellar mass and see that there's still a large amount of scatter in stellar mass for a fixed Vmax. So that's good to know that it's not just that the previous relationship isn't just due to tidal stripping. We see that there's still a huge amount of scatter in both of these different simulation sets. So once again, it would be great to do this for Vmax peak, and these results are for redshift 1. And I'll be doing subsequent analysis on the time series after I generate the merger trees for these simulations. If we look at the gas mass and stellar mass of our halos, we see that they're in agreement with the alfalfa survey generally, but this is the total gas fraction of these dwarfs, and we haven't looked at the temperature dependence of these dwarfs. So it'd be great to look and see if we just select for cold gas, what it looks like, how low our gas fractions go down then. But once again, we see that these dwarf galaxies are looking pretty good with all the observations we're able to compare against at this point, which is promising, but we still need to do more analysis. So the most exciting thing, I think, is the star formation histories of our dwarf galaxies. So if we look at the star formation histories of all the dwarfs around a single vela, we can make a plot of the range of star formation histories, which is this gray curve. So that's the range of all the star formation histories for all the satellites of a single host galaxy in this mass bin. So I've selected them into different mass bins, and then you can see the black line is the average of all those star formation histories. And we can compare them with observations from local group dwarfs. So here I've plotted some of Dan Wise's observations of the cumulative star formation histories of dwarf galaxies in blue. And you can see that at various mass bins for this vela, and this is representative of all the velas, this is just the first one. So I put those plots up here. You can see that we're in agreement with the average observed star formation histories of galaxies in the local group. But we also find a huge amount of scatter, right? This gray area is enormous. So we also find that there is a wide variety of star formation histories in our dwarf galaxies. So in order to compare with all of the velas, since I have here only a single host, what I'm going to show you is this black line, which is the average for all the dwarfs around a single host galaxy. And I'm going to show you all of the averages for all 10 velas. So once again, we're in a single mass bin. So these are all subhalos of a primary galaxy in this mass bin, and all field galaxies, where field is just outside our veer, of a single mass bin. And we have each line, so all the gray lines, there are 10 of them. That's one for each host halo. So if we look at the star formation history, I was a little surprised that the differences between just radiation pressure and including this photoionization model don't look so dramatic, but this is just the first mass bin. So we notice one other thing that I find interesting is that in the field, our galaxies have built up their stellar mass extremely quickly, even faster than the subhalos. So we see that at 13 gigayears, so we have 90% of the mass is built up already for these field galaxies. And if we step up in stellar mass, we can see that the field hasn't changed that much. Maybe the tail end of the star formation history is a little bit more extended. But our subhalos are starting to look a lot smoother, and the black line is just the average of all these gray lines. So you can see we still have a huge range of differences in the individual star formation histories of the galaxies. But on average, there's some trends where it's looking good, and all of these lines compare very well with the data provided by Dan Wise, but it just would get really overcrowded if I included all the lines. So in these larger objects, we see a much smoother star formation history beginning to develop. This is a little bit interesting here. This seems to be the first by eye difference you can really distinguish between the two models are in the field. And for our largest, most massive galaxies, they have almost a constant accumulation of stars over their history. So it's a continuous buildup of stars up to redshift 1. And it looks like, although there is still a large range in variation in the star formation histories of each galaxy, it looks like they're agreeing with the main trends of observations. So one thing we can look at, which is something that Danielle and I were just talking about this week, is how can we more quantitatively look at the differences between these galaxies. So these different subhalos, what we can do is we can take a single vela, so we can take one host halo from just the radiation pressure one and divide the two different feedback models. So we can say, if we look at the cumulative star formation history for one host galaxy, and if we divide the model with radiation pressure and photoionization by the one with just radiation pressure, we can look at how the star formation histories have changed with time. So this is just for subhalos I'm showing you here. And so this is some way we can figure out what's actually happening that's different between these feedback models. So in each stellar mass bin, you can see that the ratio of the star formation histories for each of the host halos, you can see that there's a lot of difference at early times, and it quiets down towards later times. And as you step up in stellar mass, we see that there is a larger change in later times in the galaxy's history. And for the largest mass galaxies, it looks like there's actually a difference in the star formation histories between just the pure photoheating and the radiation pressure model. So that these are these two lines, up here, the subhalos. So it actually looks like there's some differences between the most massive subhalos when you choose which feedback model you use. So this is pretty interesting. And we would love to do this at redshift 0. So we have created some new initial conditions. Angela just created some new initial conditions, and we're calling these the Vela 4s. So we're having, both of us are going to be running it over the next year. We've already run 3 sets of galaxies down to redshift 0. This includes all of the physics I've talked about earlier, supernovae, radiation pressure, and photoionization. And we've included a deterministic model for star formation instead of a probabilistic model for star formation. These are all from the same box of 100 megaparsecs on the side with a resolution of 60 parsecs. So, and we've once again not selected for any specific environment, and so some of these have some major mergers at the end, and we'll be hopefully running about 50 of these galaxies. Right now, 3 are to redshift 0. And so here's a nice image of what it looks like at redshift 3. So you can see there's a lot of structure. This is a gas density projection of one megaparsec on the side. So there's a lot of stuff going on, and it's going to be really exciting to start looking at these new simulations so we can look at the population of dwarf galaxies at redshift 0. So in conclusion, we've talked a lot about the Vela simulations at this conference, but we haven't yet talked about the dwarf satellite population around these galaxies. Now I've shown you a little bit about their star formation histories, about the abundance of these satellites that we have at redshift 1. It looks like models of radiation pressure and radiation pressure plus photoionization produce similar looking dwarf galaxy populations. Maybe the biggest difference is the abundance of low mass satellites, of low mass luminous satellites, and there's possibly some differences in the early star formation histories of these dwarf galaxies. So we still find a huge spread in stellar mass to halo mass relationship, and I'd really like to look at that more because this has implications for scattering in the abundance matching relationships, which I'm sure Shay will talk about in, I guess, an hour or two. So this is pretty exciting, and we're glad to be running new simulations down to redshift 0. Thank you.
We have time for a question. Mark?
Can you say a bit more about your tau IR, how it's computed?
I don't know if Danielle wants to go into the details. It's the same that it's been for like the last 2 years of talks. The tau IR.
How's your tau IR computed? Where's it coming from?
Okay, so the tau IR is depends on the optical bit.
Okay, optical depth using what opacity for the dust? Okay. Okay.
Okay, let's thank Kenza again. Okay.
From Sebastian and, of course, Joel. So the simulation set I'm going to be talking about is the VLA simulations that we've heard a lot about during this conference. These were run by Daniel Severino using the ART code. They were not selected specifically for any Redshift 1. So all the results I'm going to be talking about today are Redshift 1. So what I'm going to be showing you is a comparison between two different runs of the same initial conditions. We've heard a lot about the velas with radiation pressure and supernovae feedback. The radiation pressure has only trapping of ionizing photons, no merger, no late merger at redshift 1, but that's the only selection criteria on the environment or the merger history. They have a range of virial masses in the objects I'm going to be showing you. The primary halos, there's 10 of them, and they're in the mass range of 10 to the 12 to 2 times 10 to the 11 at redshift. No IR photons, so that was the Vela RP, which has been called Gen 3, which is also Vela version number 2, which you guys have heard about a lot throughout this conference. But very excitingly, Danielle has run the simulations again, and they've just finished. And this is Vela radiation pressure plus photo. We're getting towards the end. That's both good and awesome that this conference has gone so well. I'd also like to thank the Blue Waters Graduate Fellowship, without which this research wouldn't have been possible, as well as the other people that helped me with this work, especially my advisor, Anatoly, Danielle, who you just heard.